Hello everybody, we're going to continue our work on shear strength of soils, and you recall, so this is shear strength. And we had discussed last time the pole method, which is a method to find stresses on a plane, or to find a plane where some stresses are acting. So the idea is we'll practice the pole method, which is a method, a graphical method, to find stresses on a plane or the plane on which some stresses are acting. Okay, and we're going to practice this, but before we do that, I want to go over what I talked about last time, which is how to first find the pole, and then what the three components that are essential to this pole method. So to find the pole, and that's usually the first step. Maybe I should first, let me here put the pole is a point on the Mohr circle which has specific properties. And we're going to see what those properties are. But these properties are such that we can accomplish what's described here in the pole method. So the first step will be to, and we're going to practice through some example, but the first step will be to find the pole. So the first step is to find a plane where stresses are known. Okay? So whether we're in the direct shear test or a triaxial test, we need to find a plane where the stresses are known. Then we find the point on the Mohr circle corresponding to that plane and the associated stresses. So these stresses will be, in the Mohr circle, the Mohr diagram, we have a set of stresses which are the normal stress and the shear stress. So we find that point, then we draw a line parallel to the plane, going through the stress point. On the Mohr circle. Okay? So now we have a plane, we have the point on the Mohr circle, and to find the pole, and this line that we drew in step number 3. This line intersects the circle in 2 points. These 2 points are the stress point because you just drew it through the stress point. So that point is on the Mohr circle. And the other point is the pole. So that's how you find the pole to this process. So whatever you do, when it comes to the pole method, you always have 3 very important components. And these components are, 1, the plane on which the stresses act, on which you have sigma and tau. 2, you have the stress point on the Mohr circle. So the stress point on the Mohr circle will have an ordinate of tau, an abscissa of sigma. So again, sigma, tau are the coordinates of the stress point on the Mohr circle. And then the third component is the pole. And in any problem that deals with this issue here, a method to find stresses on a plane or plane on which stresses act, you always have these 3 components. And you need 2 of those to find the third one. So since at first you don't know the pole, you got to have these 2 to be able to find the pole. So that's what I say, find a plane where you know the stresses, then find the point on the Mohr circle corresponding to that plane, and then you can find the pole. That pole is a unique point. So here I should say is a unique point. So once you find it, you're good to go. It's not going to change. It's a set point on the Mohr circle. So once you have the pole, then, and you're given a plane, for example, you can find the stresses on that plane using the pole method and that point here. If you have the pole and you have the stresses, you can find which plane those stresses are acting on by using the pole method. All right, so let's practice this. And the first problem I want to do, I want to go back to the problem we did on the direct shear test. So this is problem, I'm back to, I want to do it here. So I'm doing problem 9.16, page, let's see, 229, page 229, and this one was dealing with the direct shear test, okay? All right, and we were in, so let me go to this, page 229, 229, there we go. And so we've already done that problem up to a point. And we had found, let's see, we had found that we had, and we're going to select, let's see, we're right here. So we had 2 points. We had tau of 25 and sigma prime of 30. So we had 2 tests. The first test, test 1, had tau equal and sigma prime equal. So this is both in kPa. Tau was 25, sigma prime 30. So it's 25 and 30. And we had test 2, where we had tau of 40 and sigma prime of 60. 40, sigma prime was 60 kP, both of those. And the question that we're going to ask, find the principal stresses and the planes on which they act. All right. So we're going to do this, and you recall that what we had done is we put on the tau versus sigma prime set of axes, the more circle set of axes, those 2 points. So we had one point here that say, oh, I got to put the units, so we're going to go to 60. So 60 is, let's see, I'm going to have to do this, so I better put 50 right here, and then 100 right there, and this is sigma prime in kPa. And then I've got to have the same units here, so this is going to be 50 as well. And these were the shear stress and effective normal stress at failure for that particular direct shear test. So at failure, I had 25 and I had 30. So 30 is right here, and I had 25 right here. Okay, so I had 1 point right there. And then I had another point at failure where tau was 40, so right about here. And then sigma prime was 60, so right about here somewhere. Okay? And that was the second point. Because these 2 points are corresponding to failure in shear, they must be on the failure envelope. And therefore, that failure envelope being a straight line, remember the failure envelope says S equal C prime plus sigma minus alpha UW times tangent phi prime. And this right here is sigma prime. That's a straight line. S is the maximum value of tau. And then sigma prime is here, so the slope is tangent phi prime. That's a straight line. So I can put a straight line through this. And that blue line is the failure envelope in shear for the soil. The first question is find the principal stresses. Okay, so we're going to deal with the first test, the test 1 right here. We're going to do the calculations for test 1. All right, the one that's in red, the red point right there. So the element, the direct shear test element, has a Mohr circle associated with it. This point is a stress point on a plane within the direct shear test. Therefore, it's associated with a Mohr circle. And the question is, where is the Mohr circle that can describe all the stresses on planes within the direct shear test? This Mohr circle cannot be under that blue line, because then we wouldn't have a failure anywhere in the sample. That circle cannot be intersecting the blue line, because we'd have some stress points that are beyond the failure line, and they would have failed before they got there. So therefore, the Mohr circle has to be tangent to the blue line. So what we do is we take the perpendicular to that blue line going through this point, and that gives us the center of the Mohr circle. And then we complete the Mohr circle, and that gives us the Mohr circle for that test 1 here, test 1. And this would be test 2. Now we're going to do the same thing for test 2, but we'll stick to test 1. So then, what are the principal stresses? Well, you know the principal stresses are the stresses that are on planes where the shear stress is 0. So this is going to be sigma prime 3, and this is going to be sigma prime 1. In the direct shear test, remember that that test, I'll draw it here, that test is like this, and then we have a shear plane in the middle. We apply sigma prime this way, and then we push in one direction, we resist in the other direction, and that's how we shear the sample, and in this case, the sample would move in this fashion. And the plane of failure is right here. Now the second part of the question is, what planes are the planes on which these normal stresses are acting? Pole method, typical graphical method to find stresses on a plane or plane associated with stresses. In this case, we know the stresses, sigma prime 1 and sigma prime 3, but we want to find what planes these stresses are acting on. So the first step is to find the pole. So step 1, find a plane where the stresses are known. Which plane do we have where we know the stresses? Well, it's there's only one actually. It's the horizontal plane, and on that horizontal plane, which is the plane of failure, we know the effective normal stress and the shear stress, which happens to be the shear strength as well. So that's this point right there. That's the stress point and the plane that we know. Find the point on the Mohr circle, so that's what I just did, step 2 over there, corresponding to that plane and associated stresses. So these are the stresses. The plane is horizontal, the stress point is here. Step 3, draw a line parallel to the plane going through the stress point on the Mohr circle. So through this pair, I draw a line that is parallel to the plane on which the stresses are acting. That line, step 4, intersects the circle at 2 points, the stress point and the pole. That line intersects the circle at 2 points, the stress point and the pole. We found the pole. The pole is right here. Then, once we have the pole, we're back here, we're at the pole, we know the stresses, we know the pole, so we knew 2 and 3, we can find the plane on which the stresses are acting. How do we do that? We know that a line that joins the pole and the stress point will be parallel to the plane on which the stresses are acting. So if I draw that line, then I know that that line is parallel to the plane on which sigma prime 3 is going to be acting. So therefore, that line right here, which is parallel to this plane, is going to be having sigma prime 3 on it. And then, if I want the plane on which the pole is acting, then we are going to have a line that is parallel to this. So that line is right here. And sigma prime 1 is going to be, so that's the big one. Sigma prime 1 is acting in this direction. So that's how we use the pole method. And that helps us, in this case, to find the principal stresses and to find the planes on which these principal stresses are acting. I want to do a second problem, and The second problem has to do with the triaxial test. So let me see. I'm going to, I guess I'll erase this. So triaxial test, you remember, it's a cylinder, and we're going to take a cylinder that looks like this, and we have a stress sigma 1, which is made of, let me show the components here. We're going to first have sigma 3 all the way around the sample. And then we're going to increase the vertical stress by Q divided by A, so that this quantity right here will be sigma 1. And then this is sigma 3 as well. Sigma 3 here and sigma 3 there. Okay? And we're going to fail this sample by increasing the vertical stress on the sample. So I want to do problem 926. And so problem 926, problem 926, let's see, that's page 236. And we did that one last time. we got all the calculations of the principal stresses and so on. So I'll just write down, let's see, let me go to page 236, 236. Right here. And the results were the following. So we had more circle that we had obtained, and so again, tau and shear strength, maximum value, and then sigma prime right here. And we had found that the stresses went to 600 here, so 300 here, 300 here, 300, 300, 600, and this is in kPa, and this also is in kPa. So 200, 100, 100, 200, 400, 500. Okay, so that's the Moore set of axes. And we had found that the principal stresses for, let's do test 2 from that problem. So the principal stresses for test 2 were 210 and 600. So test 2, I had sigma prime 3 equals 210 kPa, and sigma prime 1 was 600 kPa. All right, so 210 is right here, and 600 is right there. So then I can draw the Moore circle. And I have a center at 415. So somewhere in here is the center. And then this is sigma prime 3, and this is sigma prime 1. And we had another circle, another test that was here, such that we were able to draw the failure envelope on those two circles. Let me just briefly put the other one in dashed line. It goes from 80 to 250. So from 80 to 250 is right here. So we have another circle that's like this. And so the blue line is the tangent, the common tangent to these two circles. And it goes like that. And I gave us C prime and phi prime for that particular material. Again, the equation that you need to recall is S equals C prime plus sigma minus alpha UW tangent phi prime. All right, so the point of tangent C is right here. And we want to apply the pole method because the question is, what are the stresses on a plane? What are the stresses on a plane which makes an angle of 30 degrees with the horizontal? So the question is, here's the plane. What are the stresses, sigma prime and tau, within that Triaxial test? Pole method. And remember, pole, stress point, and plane. We don't know the pole, we got to find a plane and a stress point that we know. Well, we know that we have a horizontal plane here, and sigma prime 1 is applied, is acting on that. Actually, these are total stresses, but you have the pore pressure inside so that you, and that's what we did in answering those questions before. But we know that sigma prime 1 is acting on the horizontal plane. So we know the stress point, we know the plane, we draw a line parallel to the plane going through the stress point. So the stress point is here, and I draw a line that is parallel to the plane is horizontal. So I draw this line, it intersects the circle in 2 points, the stress point and the pole. So here is the pole. So now we have found the pole. The pole is unique, so we're good to solve any other problem associated with this. The plane that we're interested in is the plane that makes a 30-degree angle with the horizontal. So then through the pole, which I just found, I can draw a line that is at a 30-degree angle. So that line is, it's not parallel to the blue line, that's just, it just so happens that it looks like it is, but it's not, okay? That line intersects the circle at 2 points, the pole and the stress points, okay? So therefore, the stresses that act on that particular plane right here, tau and sigma prime, are these stresses right here, tau and sigma prime, that are acting right here. And then we can read them graphically. So would you say this is 100 and maybe 160, something like that? And then this one is 3, 4, 5, maybe 510, okay? kPa. And this is kPa as well, okay? So that's how we find the answer to those types of problems. And again, very likely you'll get one of those at, on the final. I could have I chose the horizontal plane here, and sigma prime 1, because sigma prime 1 was acting on the horizontal plane. I could have chosen, I know another plane, another stress, which is sigma prime 3. I could have chosen this one. In that case, I would have had the line would be vertical, the stress point would be sigma 3, and I would have to draw a line, vertical line, that would intersect the circle at the stress point and the pole. In this case, the line is a tangent to the circle, so the two intersection points are the same, sigma prime 3 and the pole. So the pole, that demonstrates that, that shows that for those two planes, the pole is the same, and then I wouldn't have changed the solution to the problem. Okay, so that's two examples of the pole method. Now I need to change to another topic, and that other topic is called undrained shear strength. And it's a special case, so I want to erase this. Actually, I can erase everything. So undrained shear strength is a special case where the material does not drain. That's what's called undrained. And it's particularly useful in the case of fine-grained soils. So soils like silts and clays that typically, when you load them fast, don't have time to drain, at least for a good while. So that would be the case, for example, right after construction of a major structure. So we'll write it here, special case of the undrained shear strength. And while it's a special case, it's actually very useful in a lot of the things that we do. So, to present this special case, I'm going to page 455 in the book. So page 455, section 15A1. So section 15.8.1, page 455. Okay. So here, the issue is this. If you deal with a material where you have, and you know in soils we have two components. And first of all, sorry, that's my phone. I need to turn that off. 1, 2, 3, off. All right, good. Sorry about that. So this is a special case of undrained shear strength for fine-grained saturated soils, where we actually apply it to other types of soils, but the main application is saturated soil and fine-grained soils. So imagine that you have, and so for the saturated soil, you have two components. You have the skeleton and you have the water. The water for these fine-grained soils has a hard time draining out of the small pores in that soil. And so you have the two components. You have the skeleton that has a certain stiffness, and you have the water that also has a certain stiffness. And in the undrained behavior, if you think of trying to compress by applying a load, the two springs, so here you have a stiff blue spring like this, which is the water. And then you have a weaker spring, which is the skeleton, or let's call it the soil skeleton. Okay? So if you apply a load to this system, you have a stiff spring and a weak spring. If you apply that load, most of the load will be carried by the stiff spring, because whatever deflection you have, the stiffness is such that a lot of the load will go to the blue spring, and very little load will go to the soil skeleton. So what happens, and let's say that this load is applied in the construction process. So you can say that before construction, you have an effective stress, which is sigma prime B, B for before, equal to the total stress, sigma B, minus the water pressure before. Okay? Before construction. After construction, you have applied this big load Q right there. And it's relatively fast. Not that construction is fast. It may take a year, but it may take 20 years for the water to drain out of the fine-grained soil. So essentially this load that comes on the soil loads the water, it goes into compression, and the blue spring catches all the load. At the beginning, the load is carried by the water. Now that might seem a bit surprising, but the problem is that the water cannot escape from those small pores, and that's why it's an undrained behavior, and the water carries the load. So if the water carries the load, after the effective stress after construction is going to be the total stress before plus the increase in stress due to construction, the increase in stress due to the building, minus the pore water pressure before, plus the increase in water pressure due to the construction. And because the blue spring is much stiffer, all the water pressure is going to be the one carrying the delta sigma. So this is an increase in the water pressure equal to the delta sigma. And so when you simplify this expression, you get sigma prime A equal, the delta sigmas will cancel, and you see that you get back UWB. So this is sigma prime B. The effective stress has not changed. And that's bad news, because you remember from the shear strength equation, you remember this important equation, S equals C prime plus sigma prime tangent phi prime, right? This thing. If you don't increase this, you don't increase that. And so that's what's happening with the undrained shear strength in this case. So we're going to write this specifically for saturated, and we'll say normally consolidated, okay? Normally consolidated fine grained soils. Fine-grained soils. The undrained shear strength, is because the effective stress does not change. Okay? So in essence, and I'll do the diagram right here, in essence what happens is that if you have the more Coulomb set of axes, shear stress, effective stress, and on this set of axes you have a Moore circle that looks like this, and then you run a first test and you plot something that you shouldn't plot, in my opinion, and you happen to plot it versus the total stress. If you plot it against the total stress, that circle will come out right here. Whoops, let me put it in blue. All right, that Moore circle will come out here. Why? Because the total stress is equal to the effective stress plus the pore water pressure, or if you prefer, so this is going to be sigma prime 3, so when I go up this way, I got to subtract the pore water pressure, UWB, and that gets me to this stress right here. If I now do another test at a higher total stress, sigma B after construction if you wish, I've increased the total stress to sigma B plus delta sigma. So now I've got a green circle right here. And I find out that the circle has the same diameter. Now the blue one was at sigma, what did I say? Sigma B. And so this would be sigma prime B, because I'm subtracting UW. And then I increase to sigma B plus delta sigma. So the green one here is associated with sigma B plus delta sigma. But the water pressure has increased by delta sigma as well. And it's equal to UWB plus delta sigma. So I actually go back to the same value. In other words, even though I've got a different circle on the total stress set of axes, I've got the same circle in the effective stress set of axes. And it looks like this undrained shear strength is a constant in the total stress set of axes, when in fact the effective stress is guided by the same expression, which is right here, and it given, so you can actually express the undrained shear strength by this equation, which always works. Okay? But this is a special case, and it turns out to be pretty useful. And I'll finish by one example. And this example is sort of tied to the Tower of Pisa. So let's go back to the idea of the Tower of Pisa. And so here we are. We have a big tower that's being built, and we're going to calculate the ultimate pressure that you can place under the Tower of Pisa. So we have a pressure right here, which is the maximum pressure the soil can resist we'll say P sub ultimate, P sub U. And then we're going to say, well, if this tower is going to collapse, it's probably going to rotate and make the soil rotate along a certain failure pattern. And we're going to say, well, what about a circle? So we're assuming a failure surface. And along this circle, we're going to have the undrained shear strength, S sub U. The width of the tower is B, and I'm simplifying by taking a plane strain condition, and I'm going to write moment equilibrium around O. So I'm writing moment around O equals 0 equal. I've got the moment due to P sub U, so I'm going to have P sub U, which acts over B, the width. And that will be the line load under the tower. The moment arm is going to be B over 2. Okay, so that's the moment in this direction. The resisting moment will be due to S sub U. So I'm going to minus S sub U, which is the stress acting along that circle. I'm going to multiply by the line length associated with the circle, so that's going to be pi, so the total circle would be 2 pi r, but r is b, so that'd be 2 pi b, but I've got half the circle, so I've got pi b. And then the moment arm of this resisting force is b. So when I simplify this equation, I get P sub U equal, you can see that the b squared disappear, and I've got P sub U equal 2 pi S sub U. Okay, so it's a simple way of estimating the bearing capacity of soils under undrained condition. So basically, we're talking about 6 times the undrained strength. Now, Tower Pisa. The Tower Pisa the undrained strength of the material is about 80 kilopascal. And so the maximum pressure you could put on that material in Pisa would be about 6 times 80 equals 480 kilopascal. The actual pressure under the tower was just about that value, and that's one of the reasons why it sank about 3 meters, and unfortunately, or fortunately, because they've made a bunch of money with the Tower Pisa, all the tourists, it actually tilted. So that's a simple application of shear strength. There are many more, and that are associated with this when it comes to ultimate bearing capacity. So that concludes our discussions on shear strength. The next lecture will be the beginning of our discussion about soil deformation.